Well, continuing with this type of methods of welding, now we will talk about submerged arc welding. Right. As you can see, submerged arc welding, also referred to as SAW, in simple also is referred to as SAW, submerged arc welding. Well, just by the way, I mean submerged arc welding does not mean anything to do with underwater welding. It has nothing to do with underwater welding. This term submerged means the arc is submerged, not the entire welding process is submerged. When the entire welding is done submerged in water, that is what is underwater welding. So, here the welding is done above water, it is nothing to do with underwater welding, only the arc, molten pool, these are submerged in flux. That is how the name submerged arc. Previously, all the welding processes till now we have seen, in all the processes the arc is kind of exposed, it is not submerged. If at all it is submerged, it is submerged in gaseous medium. So, it was visible always in all the previous welding processes. One will have to use proper protective means in the eyes such that you do not affect your eyes, because that is a very intense light source. A welding arc is a terribly intense light source, right. If you look at that, eyes will get damaged severely. Here in this submerged arc welding, you do not see the arc, because the arc is submerged in a pool of flux, right. There is a fundamental difference in this method. So, as we see what are its basic features? First and foremost, as we see that it is a fully submerged in flux, right. Thereby what you get immediately? The immediate benefit is heat loss is minimum. Heat loss is minimum, like I had been just showing here by these arrows. These are basically radiation loss, convection loss, right. Whatever heat is coming in from the arc, part of the heat is getting conducted in the plate, right. Thereby your fusion is taking place and rest of the heat is getting lost by conduction. Some of the heat is getting lost through radiation, convection from the plate surface, from the molten pool surface, right. Whereas, here in this case that does not happen, because it is all covered by a shield of flux, and that flux being a insulating kind of medium means not a conducting medium, its thermal conductivity is low. So, heat loss is minimized, that is one of the biggest benefit. Another benefit obviously is to the welder, means that you do not see the arc. So, chances of damaging your eyes are very is not there. Right. Thermal efficiency is as high as 80 to 90%. What is this thermal efficiency? It is, you see, when we talk about the welding heat, in welding there is something called heat input, that how much heat is going in the plate, that is given by Q. As I said, this is V into I, right, but the actual heat input is multiplied by some eta. That eta is the so called thermal efficiency of the process. What is that? This is actually the heat which is, this determines the how much heat is actually going into the plate and how much is getting lost. So, eta for submerged arc welding, as here we have mentioned, is around 0.8 to 0.9 for submerged arc. Similarly, say for manual metal arc welding, it is of the order of, well, around 0.7. Shielded metal arc welding. Tell me, how much do you think it should be for gas metal arc welding? Why so less? 0.5? Well, tell me whether it will be more than 0.9 or less than 0.7 or will be in between. Why should it be in between, not less, or why it should not be more?
It should not be more because heat is free.
Well, straightway cannot be more, because here we have seen that it is a process where I am saying the heat loss is minimum, the arc is properly covered, and there the heat loss is maximum, because I am injecting a gas. You see, in shielded metal arc welding, the gas is generated by burning the flux. So, that kinetic energy of the flow of gas is not that high. The flux burns, gas is formed, and that gas is giving the shielding to the arc in manual or shielded metal arc welding. But in gas metal arc welding, I am pumping in gas. So, gas by force is going and going away. So, it is by convection, it will take out lot of heat. So, heat loss is more. So, it is not that low as 0.5, but it is of the order of 0.6 to 0.6.5, I mean 0.65. So, gas metal arc welding, there is a lot of heat loss, because this is important. Why important? With that much of thermal energy, because I am burning the same amount of energy, but utilization is less, 40 to 35% is going off, right. Whereas, the heat energy utilization is much better, 10 to 20% is only lost, right. Anyway, so this it produces no visible arc light, as I was saying. That is also one plus point of this submerged arc welding. It is very welder friendly. There are hardly any fumes, right. No need for fume extraction, as you can see. In shielded metal arc welding, shielding, what you call coating material over the electrode is so designed that it will produce a gas, it will produce a fume. So, you will have to have a fume extraction mechanism, because that otherwise it will be a hazardous for the operator. So, here you do not need any such thing, because hardly any fume is generated, because we do not intend to generate any fume. So, the flux is also accordingly prepared that it produces minimal gas. One can have a high deposition welding. Why? Because this process is essentially automated process, and being automated process, I can give higher heat, higher current I can use. Once higher current, you can go for a high deposition process. And it is another feature, it is always a downhand welding process, means it can weld only downhand, not those positional welding of vertical or overhead. What are the operating characteristics? It is a fully mechanized process. Here also the electrode acts as the feeler wire, right, unlike tungsten arc welding, right. Like SMAW or GMAW, it is also the electrode itself is the feeler wire. It is fed continuously by some feeder mechanism like you have in GMAW. Flux is fed directly on the arc from a hopper. From a hopper the arc comes. This arc heat burns some of the flux, right. The electrode tip and the adjacent edges of the base metal are melted, right. It burns some of the flux, the electrode tip and the base metal are melted, creates a pool of molten metal just below the arc, which is covered by a liquid slag. That liquid slag is nothing but the burnt flux, right. So, let us schematically one can show it like this. This is your electrode, right. Here you have the arc. So, what I have shown, of course, the diagram is not very perfect. This is the this is the plate top surface. So, I have shown a very small arc length. This arc length is essentially to the bottom of the weld pool, as if this is my bottom of the weld pool, this is the deposited metal going. Anyway, this is a continuous feeding mechanism power is fed here through this bush. There is a hopper where from where you put the granulated flux. That flux burns and forms a layer of slag, right. So, that arc heat will burn the flux. That burnt flux in the malt is slag. Now, that slag in molten condition is a dense lighter than the weld metal. So, it will float up and provide a full protection from the atmospheric oxygen. And since the liquid metal is covered with a liquid, another liquid slag, so you get a very smooth surface of the weld bead. The top surface of the weld bead becomes very smooth. So, that is also a very good property aspect of this process. Slag floats on the molten metal, right, and thus completely shields the molten zone from atmosphere, as well as it dissolves impurities of the base metal and the electrode and floats them on the surface. So, any impurity there also gets removed, kind of gets removed. The slag shields results in a slower cooling rate. That is another aspect, because when you are gradually welding it, so what is happening is how the process goes something like this. Well, suppose this is my plan view. The electrode is moving along this direction. So, the deposition is taking place, right, and if I see in the cross section, suppose this is my fusion has taken place, this is the metal deposition at the top, and then you will have over that a layer of flux like slag like this. This is the slag, means as you are going past this green lines, I am referring to the solidified slag. It will solidify, right, and then on top of that you will have these granules. Because as you see, this is continuously being fed, right, those granules of flux, and now some flux is burnt, not the entire amount. Some of it is burnt, I mean in that arc heats, a part of it will burn and will form the slag. That slag will float up on the above the molten metal and will form a solid crust. That will be again shielded with a unburnt, unused flux. Later you can recycle it. So, there, but what is happening in the process? You have a total shielding of the molten metal, of the deposited metal rather. The molten metal eventually becomes the deposited metal, solidified metal, right. So, the heat loss from here is minimal. It is having a insulating, a kind of shielding, isn't it? So, this slag shield along with the flux in fact lowers the cooling rate of the deposited metal. The cooling rate is reduced, and once the cooling rate is reduced, it provides an annealing effect of the weld deposit. What will that annealing effect will help in? It will help in increasing ductility. Chances of crack formation are lowered, because welding is a thermal process. So, that there will be a thermal stresses. So, if the material is ductile, then there is a chances of cracks forming because of stresses will be reduced. So, that is the general feature of this process. What are the power source used here? Generally a constant voltage power supply is used with electrode positive. Why? Constant voltage, because it is a constant feeder mechanism. Electrode is fed continuously, automated fashion. So, I can keep the arc length constant. So, if that is so, then it is better to use constant voltage power supply and electrode positive mode. Why? I want to deposit more metal, because increasing penetration by making DCEN, I can increase the penetration, but that I do by increasing current, and keeping the electrode positive, I melt more electrode, thereby increase the deposition rate, because I have to increase deposition rate, I have to increase welding speed for increasing productivity. So, it operates it CV or constant voltage power supply with DCEP mode, right. This is the schematic representation. Operating variables are again, see the current, voltage, speed, electrode diameter, electrode extension, length of the electrode, we have talked about it, type of flux, width and depth of flux layer, that is also is important. Too deep a flux layer again is not good. That means, here that hopper height, how if the hopper height is much above, then too much of flux will fall. That means, if say this flux layer is very huge, right, that is also not good, because that will add weight to the molten metal. So, there will be contamination of the flux, isn't it, because the molten slag should float up, but if it is loaded with unburned flux too much, it will add pressure. So, the molten slag will not be able to come up, that will give rise to slag inclusion, a defect called slag inclusion. And then finally, polarity also is important because of that heat generation. Here you see, if the welding current is too high, then obviously excessive depth of penetration, right. Too high a current will lead to excessive depth of penetration, excessive reinforcement leading to wastage of electrode. Either, I mean, high current will have a much bigger penetration. If the speed is low, then again I will have a too much of melting, right. Both are not, I mean, nothing excessive is desirable, that is the thing. These are only what we are trying to show here is, current too high means we are taking all other parameters remaining constant, all other parameters remaining constant. If you increase the current too high, then you will have all these effects, increased heat affected zone, increased weld distortion. Whereas, the current, if it is too low, obviously inadequate or incomplete fusion, right. Also unstable arc, that means arc going on and off, that is unstable, it is getting on, it is getting off. So, this is somewhat schematically we can see that with this wire diameter, this speed and this voltage, arc voltage for a lesser current, and as we increase the current, right, it is nothing but, that means increasing current, keeping all other parameters constant, it has the primary effect on depth of fusion. So, if depth of fusion has to be, certain depth of fusion has to be achieved, then you have to change the current, either you have to increase it or decrease it. Arc voltage influences the shape of fusion, primarily the external bead appearance, right. So, what you see, if the voltage is low, you have a narrow bead, if the voltage is high, you have a wider bead, for all other parameters remaining constant, right. Say the diameter, ampere, speed constant. So, less voltage narrow, higher voltage wider, depth of fusion more or less same. So, if arc voltage is increased, you have a flatter and wider bead, it will have increased flux consumption, that is also another important, because wider bead means more flux is getting burnt. Of course, reduction of porosity caused due to rust or scale on the base metal, this is the advantage. Increased tolerance of root opening, that is one thing. When we do welding, if the root opening is not very uniform, then a wider bead is preferable, because where the gap is more, I cover that, right. So, when it gives us a higher tolerance level of the root opening. That is what helps to bridge an excessive root opening. Increase in pickup of alloying elements from flux. This is one aspect in submerged arc welding that is not available in other process. Here the composition of the weld deposit, this composition of the weld deposit can also be altered, right, by choosing a suitable flux, that means a suitable wire flux combination. Wire flux combination means wire is the electrode and the flux. For a particular wire flux combination, I can change the composition of the weld deposit. There can be cases that you are welding a certain type of steel, right, and you have very stringent requirement of the joint, welded joint, that it should have so much of tensile strength, so much of impact strength, and so on and so forth. So, you may need in the process to have certain alloying elements more in this to achieve those desired properties. Say you want somewhat higher level of silicon. So, what do you do? I choose a wire which has silicon, I choose a flux which also has a higher level of silicon, such that in the process some silicon from the flux will diffuse in the molten metal. So, that is what is pickup of alloying elements from flux. If arc voltage is increased excessively, increasing arc voltage excessively means what? Increasing the arc length. This is becoming the distance between the electrode tip to the job is increasing. So, what will happen? It will produce a very wide weld bead, right. It may make slag removal difficult in grouped welds, means V group, you are welding it, the slag may remain sticking to that. Increase undercut along the edges. There is a defect called undercut, as we have seen, this undercut. Some at the side there will be a lack of deposition at the side of the weld bead, referred to as undercut. If the arc voltage is too low means what? That the length, distance between the electrode tip and the job is too low. It gives improved penetration in a deep weld group. It increases penetration. It resists arc blow. What is arc blow? The arc blow is wandering of the arc. Means if the arc length is more, arc blow is essentially, because what is that arc? Arc is a conducting medium, right. It's a kind of a conductor through which current is flowing. So, if a conductor is there through which a current is flowing, if I hold a magnet, this will get deflected. If I put in a magnetic field, right, that conductor will try to deflect. If the conductor is a sturdy copper wire or a steel wire, it will not move, but if a thin copper wire, it will deflect. Right. Same thing, that plasma column is totally flexible. It does not have any rigidity. And now, when you are welding, you are connecting the positive terminal at one point, the ground terminal at one point and the electrode there. So, it causes a magnetic field, because high current is used, 800 ampere, 1000 ampere. So, in that magnetic field, that arc column may deflect. The longer it is, chances of deflection is more. That is called arc blow. If the arc column deflects, means suppose, say purposely I am drawing a much this is my electrode, a very as if long this thing. In the magnetic field, it may get deflected like this, right. The whole arc column may get deflected. Now, if the arc column gets deflected, the metal transfer also will get deflected. So, you will have to deposit here, it will not deposit there properly. So, metal deposition becomes erratic. So, this phenomena is called arc blow. Then what you will have to do is you will have to recheck that where the other I mean the terminal, suppose you have the electrode positive here, here is the negative terminal connected. So, you have to connect at several places, I mean such that undesirable magnetic field is not formed. Anyway, but if the arc length is smaller, then chances of arc blow reduces. That is what is it saying, it raises arc blow. Now, excessive reduction in arc voltage will produce a high and narrow bead, and slack removal may become difficult. Welding speed. As speed is increased, heat input per unit length decreases. What is that? What does that mean? We have seen, I have talked about the heat input, I have said that is V into I. What is this? This is so many watts, right, or joule per second, right, so many joule per second. And now, if I divide this by speed, welding speed, then it becomes rate of heat input, right. So, if speed is in millimeter per second, then it becomes joule per millimeter, right. So, this is referred to as rate of heat input. That means, at what rate heat is going in the plate, how many joule per millimeter I am putting, because we are interested on what amount of heat is going in the plate, at what rate. Rate means not in terms of time, but in terms of the length of the weld, because we are interested in the total amount of heat going in the plate, not at what per second type, but at what per millimeter type or per meter, whatever way. So, rate of heat input is a important sort of a parameter or aspect in welding, which determines if the how much heat per millimeter is going in. If that is going more, right, what does that mean? That means this is my Q dashed, that is so many joule per millimeter. So, so much of joule per millimeter is going. If more is going in, means more heat conduction. If it is less, then it will be less. Simple. More joule per millimeter means it has to get dissipated, isn't it? That means more heat, more part of the plate will get heated up, and more part of the plate getting heated up means you have higher stresses, higher deformations, higher heat affected zone, higher melting zone. Starting from the fusion zone will be more, heat affected zone will be more, your more heat is going in. So, more thermal stresses, more deformations. So, other aspect is that if I increase the speed, this decreases, the rate of heat input decreases. So, if I want to reduce distortion, first and foremost is to see that how can I can implement a welding process which has a low rate of heat input. That rate of heat input has to be reduced, right. So, that is what we see here, that heat input per unit length decreases, rate of heat input is decreased as you increase the welding speed. So, increasing welding speed not only benefits from the point of view of productivity, but also it will benefit from the point of view of quality of the final structure. Your residual stresses will be less, your distortions will be less. Less filler metal is applied per unit length of weld, leading to less weld reinforcement. If the welding speed is low, then it may lead to over deposition. This is what is over deposition. if the welding speed is low. If the speed is low, right, then obviously more metal is getting melted and getting deposited at place. Well, if the speed is now excessively increased, right, I want to have more productivity and increase, then what will have? Lead to undercut, lead to porosity, uneven bit shape, arc blow. Why porosity? Because the gases will not be able to come out, it will not have enough time to come out, before that the metal will freeze. As I am moving the heat source faster means what? The cooling effect is faster. The molten metal will get solidified before it can, the gases can float out. So, may lead to porosity. Now, the reverse, if we decrease the speed, then heat input per unit length is increased. That is the first foremost effect. More filler metal is consumed, leads to more weld reinforcement, right? Increased penetration, but not much. It is not a direct effect, because the same phenomena will work, the same cushioning effect of the molten metal will work, but provides more time for gases to escape, thus reducing porosity. Chances of porosity will be much less. Further, if we reduce, well, very convex bit shape, more prone to cracking, large molten weld pool resulting in rough bit, slag inclusion might take place. Weld penetration is not further increased, as we have talked about. Penetrating force of the arc gets cushioned by the molten pool, right. So, this is schematically tried to show that say here is the 25 millimeter per second, 13, 6, I mean how for the same parameters changing like the depth, just by doubling this, here it was 13, it is 6, as if the speed is halved. So, what has happened? It has become wider, but depth has not increased. Electrode diameter, here it is a high deposition welding, so one can use much higher dia electrode. As you can see, you can go even 5.6 millimeter dia electrode, more thicker electrode. So, you can deposit much more metal. So, what you see that the weld bit shape and the depth of penetration are affected by electrode diameter, what electrode diameter is used. Higher diameter electrode can carry much higher current, so thereby high deposition rate, right. Now, in this what we have tried to show that other parameters keeping constant, because when I use a high diameter electrode, essentially I should increase the current also, because otherwise there is no, I mean the purpose is not served. Once the electrode dia is high, it is capable of carrying more current. If that is so, I increase the current, thereby I melt more metal, I deposit more metal per unit time, and thereby increase the welding speed, I increase my productivity, right. Now, if I do not do that, I keep all parameters same and just change the electrode dia, then the effect is this. The whole idea of showing this diagram is that with lesser dia you have a higher current density. Lesser dia electrode current density is higher. For the same current condition, say here in this example is for 600 ampere current, 30 volts and 13 millimeter per second speed, with 3.2 dia I find more penetration. With much higher dia I find less penetration, but wider bead. What does that mean? That means a higher current density increases penetration, right. A higher current density increases penetration. Electrode extension, that is nothing but, we have talked about it, it is the length of the electrode beyond the, from where the power is, from the tip to the point from where it takes power. schematically it can be seen like this. Here you have the shoes where the power is fed. That means the electrode passes through this shoe where the power is fed, right, and this is my electrode tip. So, this distance is the electrode extension. This distance is the electrode extension. So, if the electrode extension is high, then we tend to then it results in higher deposition rate. For same all other parameters remaining constant, I just increase the electrode extension, my deposition rate increases. Why? Because of the additional joule heating of that. But this will be predominant, or it will have more significant effect provided the current density is above 125 ampere per millimeter square. That means, at lower current level, increasing electrode extension does not make much difference, but if my current density is above 125 ampere per millimeter square, then even deposition rates can be increased as high as 50% with no change in welding current. Deposition will increase, right, without changing the welding current. That means what? Essentially penetration will decrease, more heat will be generated in the electrode, more power will be consumed in the electrode, thereby more electrode melting will take place. Electrode extension for all practical purposes, essentially thumb rule is 8 times the electrode diameter. Say the electrode you are using is 4 millimeter dia electrode, you generally keep 30 to 35 millimeter long this extension, because go on increasing it, it does not mean that this 50% will go to 80%, no, because then what happens, the electrode length becomes too long, it becomes unstable. The electrode is getting heated up, so it will not come straight, it will get unstable. Again the same thing, it does not mean that the deposition rate will go on increasing with increasing the electrode length, no, up to a certain point it will work, then again the whole process will become unstable. There is some relation through which one can find out approximately, there are some empirical relations, so how much would be the electrode melting rate for a given electrode extension, how the electrode extension is changing. Width and depth of flux, bead appearance and soundness of the finished weld also depends on this width and depth, right. If the layer is too deep, too much of flux has been poured, that hopper position is not fixed properly, not aligned properly, too much of flux is pouring over the weld deposit, then gases generated during welding cannot readily escape, and also the molten slag will be under pressure of the weight acting over it by the flux. So, we will get a distorted weld surface. Too shallow, if the flux is too shallow, then what will have? Sparking will be visible. That means, proper shielding will not be there, you will be able to see sparks in between. That means, the layer is too shallow, that means, too little flux is coming, the flux chamber is jammed or whatever, also will result in a bead appearance, poor appearance. Now, the flux, the type of flux, what it does, apart from shielding, it acts the stability of the arc, the chemical composition of the flux acts towards the mechanical properties of the deposit. This flux is basically made up of oxides of manganese, silicon, titanium, aluminium, all those. It is essentially a mixture of all those oxides. And then you have the so called wire flux composition. I mean, for a certain welding of certain material, whatever mechanical properties are desired, use a suitable wire flux combination, as we have already talked about. There are generally two types. This just we can go fast. There is a bonded flux, bonded with a low melting compound, and there is a fused flux. This you can see later. this fused flux, they are can be used for very high current operations, also gives a consistent weld metal property. Another important aspect is the flux prior to use should be baked. The spelling is probably wrong, it is baked, that C should not be there, should be baked to remove moisture, because as you know, moisture should not be there in a weld environment, because that will lead to hydrogen embrittlement, that hydrogen will go in the microstructure. So, moisture if present in the flux will cause porosity of the weld deposit as well as cause hydrogen embrittlement. Here some of the aspects of how to estimate the weld parameters. So, if it is a square butt means the two flat plates being welded having rectangular edges. This is what is referred to as square butt. When it is welded like this, then it is called V groove, right. This is square butt, this is V groove. There are the edge preparations, various edge preparations are done depending on requirement. So, generally when welding is done, as you see, the breadth of the reinforcement to the depth of fusion, this ratio should be around greater than or equal to 6. These are some of the thumb rules. Breadth of the width of the fusion zone to the depth of fusion, right, should be around 6 times, right. And also sorry, this breadth to the height of reinforcement, that means how much metal to be deposited, what should be the reinforcement height, this and this width, right, breadth of the reinforcement and height of reinforcement. This is HR here. This is the breadth of reinforcement to height of reinforcement, that is generally 6 times the HR, and also the breadth of reinforcement is around 2 times the depth of fusion. If that can be achieved, then generally the cracks will not form, right. The joint geometry satisfying these above conditions provides better means of gas escape and also reduces possibility of developing cracks. Of course, when you will weld, it is difficult to really assess how much will be the breadth, width and how much will be the reinforcement depth, etc. These are well, if one does some analysis, some theoretical calculations prior to selecting the welding parameters, then one can use these conditions to see what are the suitable parameters. Of course, in real life case, you do not actually go for calculating the parameters, you take from standard codes. But why? Because the weldings are generally standardized, but where you have a non-standard situation, then all these factors come into play. So, for that I have given some this you can see later once we have the intermaterial, how to estimate the first approximations of submerged arc welding parameters. If you have to go for a non-standard case where you want to assess what should be the welding parameters, so there are certain thumb rules given from which you can certain empirical relations are given, wherein you can get the what would be the depth of penetration for a given current, for a given speed, etc. Right. Well, cracks in submerged arc welding, because in any, so what we see in the submerged arc welding, this is a high deposition welding process, right, high deposition welding process, it is an efficient welding process, and also it provides welding of good quality. that means the weld bead profile is smooth, as well as since I mean it's automated process. So, you can achieve a higher speed of welding, so higher productivity. At the same time, there can be a risk of cracks developing in this. Why? Because it is also a high heat input welding, though as I said, making it automated, I can increase the speed, but depending on how much deposition rate you want, deposition rate is again depends on the speed. So, if you want to have a higher deposition, then again you will have to reduce the speed. Once you reduce the speed, your heat input rate increases. So, that increases the chances of cracks forming in the weldment, right. So, that is how we see the factors controlling solidification cracking are. By means of solidification cracking means what? The metal gets solidified and you find the welding is progressing, you are going to there and you find it has cracked at the back after solidification. So, that depends on weld metal composition, weld solidification pattern, how it is solidifying, that means what is the microstructure forming inside, right. Strain on the solidifying weld, what kind of thermal stresses are forming, right. So, a parameter has been developed to calculate the cracking susceptibility depending on weld metal composition, because all these cracks, I mean which are connected with welding process, they are essentially because of thermal stresses on one hand and on the other hand lack of ductility of the material. Suppose a material is put under tension, because cracking will not develop due to compression, it will be always because of tension, right. And as you know, when you do the welding, the residual stress in the weld zone is always in tension, right. So, the weld metal zone is under tension always, and now the weld metal, if it is ductile enough, then it will take that tension and maybe will get elongated, thereby the residual stress will get consumed, right, and no crack will form. But if the material is brittle, means if the material is hard, then under that tension either it will withstand, it being too hard you cannot do anything, whatever tension, thermal tension forces are taking place, or it will crack, right. So, that is how what happens, whether it is ductile or brittle, that means it is soft or hard, will depend on metal composition, will depend on the cooling rate. Why? Because these two, the composition of the metal as well as the thermal cycle it is undergoing, that means the cooling rate determines the microstructure, and steel's property is determined by the microstructure, how the microstructure is, the size of the grain sizes, the composition of the grains, orientation of the grains. All these three together determines, actually they determine the mechanical property of steel. It is not the composition alone, it is the composition along with its microstructure. How the microstructure will depend on the composition. So, thereby a parameter that is referred to as UCS, units of cracking susceptibility. It is, as you see that, well, it is statistically it is done, it is dependent on carbon, sulfur, phosphorus, niobium, silicon, manganese contents. So, as you can see that UCS is reducing with increasing silicon and manganese, but increasing heavily with sulfur as well as carbon. That is why high strength low alloy steels has very low carbon percentage, whereas high yielding steels has a higher carbon percentage and is very difficult to weld. What does that mean? Difficult to weld means you weld, it cracks. There is a difference. Why? Because of this C, as well as sulfur and phosphorus, as you can see, they are very parameters which contributes heavily towards cracking susceptibility. That is why a shipbuilding quality weldable steel should have as low as these, as low as possible, sulfur or phosphorus. General requirement is it should be less than 0.05%, right. So, what we see that in case of butt welds, trouble should not be expected for UCS less than 25. These are some of the thumb rules. If you have within say 25, then for a butt welding it should not crack, should not develop. The shape of the weld influences the solidification pattern. To minimize cracking, the columnar grains of the solidifying metal should appear in the an upward pattern rather than inwards. These are actually the grain structure, how the grain structure should be. What happens is, you see, when a metal solidification takes place in welding, generally, well, let us assume the fusion zone is like this. So, the metal solidification takes place, the molten metal, it forms a kind of a what is referred to as columnar grains, that means grains like this. Grains like this, elongated type. So, it should have a upward sort of pattern, this upward pattern rather than downward. If the solidification pattern is like this, then it is more prone to cracking. Like it is more prone to cracking, and this is less. That means this is preferable, this is not. How that, I mean, how that will happen, that will again depend on, partially it depends on the composition, and also it depends on the parameters, right, depends on the speed. So, the tendency of the columnar grains to grow inwards, right, rather than upwards, give a more pronounced central line segregation of impurity elements. These are some of the metallurgical aspect how it happens, but it is nice to know that what basically happens, and also concentrate the contraction strain in that region. Because in this form, if it forms, then as if all the impurity elements, they get concentrated in that central region, right. Impurity elements means what? Those phosphorus, sulfur, those are the impurity elements. So, if they are in higher percentage, they will get segregated and get concentrated in the middle portion. This segregation impurity will take place, and contraction strain in the same region. To avoid cracking, consumables should be selected with low carbon and sulfur. I mean, so what is happening? Your best metal may be with low carbon and sulfur material has been used. Say that what you call HSLS steel is being used, high strength low alloy steel. Automatically, it has a carbon percentage very low carbon percentage, and also low alloying. Other alloying elements are also low. But by the process of rolling and heat treatment and the production process, they achieve a very high strength. That means suitable microstructure is achieved, fine. Now, that is being welded. So, welding consumable has to be so chosen, that is what is mentioned. So, welding consumable, that means if it is a submerged arc welding, your electrode as well as the flux should be so chosen, should have low carbon and sulfur, right, and with high manganese and silicon contents, because here you see they are the negative terms. So, if I have higher silicon and manganese, it is better for me, it reduces the UCS, that units of cracking susceptibility, that parameter reduces. So, this is what. So, that is why we see that this particular process, the submerged arc welding, is a high efficiency, high deposition process, but one of the biggest drawback is it is a downhand process. Downhand process means it cannot do any positional welding. However, as you see that to achieve a good weld quality, one should try to maneuver if necessary the jobs such that you convert all the positional welding to downhand welding. So, thereby this submerged arc welding can be, I mean in shipyards, in fact one should try to maximize the use of this particular process, welding process, because it gives you good high productivity as well as highest quality of welding. Okay. So, we stop here today.